In today's topic, we will discuss the differentiation of hyperbolic trigonometric functions. Now, before that, we need to discuss a little bit about hyperbolic trigonometric functions. So, the sine hyperbolic function of x is given by, or it's defined by, e raised to the power of x, the exponential function, minus e raised to the power of negative x divided by 2. And the cosine hyperbolic function is defined as e raised to the power of x plus e raised to the power of negative x divided by 2. So this is how we can define the two hyperbolic functions, sine hyperbolic and cosine hyperbolic. Now from here, we can define the rest of the remaining hyperbolic trigonometric functions. That is, if we consider the tangent hyperbolic function, so this will be the ratio of sine hyperbolic to cosine hyperbolic. And when we substitute the values, this will give us e raised to the power of x minus e raised to the power of negative x divided by e raised to the power of x plus e raised to the power of negative x. So it's quite similar to the trigonometric function, except for the fact that instead of trigonometric function, we have hyperbolic trigonometric function. Then the cosec hyperbolic of x, this will be defined as the inverse of the sine hyperbolic function. So that means we will have 2 divided by e raised to the power of x minus e raised to the power of negative x. Similarly, we can define the secant hyperbolic function, which will be the reciprocal of the cosine hyperbolic function. So that will be equals to 2 divided by e raised to the power of x plus e raised to the power of negative x. And we have one more, which is the cotangent hyperbolic function. The cotangent hyperbolic function will be, there are two ways to do that. So it could be either the reciprocal of the tangent hyperbolic function or simply the ratio of the cosine hyperbolic x to that of the sine hyperbolic function. And this is simply e raised to the power of x minus e raised to the power positive e raised to the power of negative x divided by e raised to the power of x minus e raised to the power of negative x. So these are the 6 hyperbolic trigonometric functions. So what we will do, we'll try to find out the derivative of each of them. We need to define the derivative of the hyperbolic trigonometric function. So let's begin with the sine hyperbolic function. We have derivative with respect to x of sine hyperbolic x. So this will be equals to taking the derivative with respect to x of e raised to the power of x minus e raised to the power of negative x divided by 2. So this will give us half multiplied to derivative with respect to x of e raised to the power of x minus derivative with respect to x of e raised to the power of negative x, which is equals to half multiplied to, so we have derivative of the exponential function, so that is the function itself, minus we have derivative of a decreasing exponential function. Here we can use the chain rule. If we assume that negative x is equivalent to x, so this will give us e raised to the power of negative x. But since this is not actually x, so we need to multiply it to the derivative of our assumption, which is negative x. So this gives us half e raised to the power of x minus e raised to the power of negative x, and derivative of negative x with respect to x, so that is negative 1. So that negative 1 will get multiplied to this minus to become positive. And this is the cosine hyperbolic function. That means derivative of the sine hyperbolic function gives us the cosine hyperbolic function. Very much similar to the derivative of a sine function, which gives us the cosine function. Next, we can try out the derivative of the cosine hyperbolic function. Now, if you recall from differentiation of the cosine function, that gives us a negative sine function. But in this case, there will be no negative sign here. So let's try that out. So for cosine hyperbolic x, we have e raised to the power of x plus e raised to the power of negative x divided by 2. Following the same procedure, we should get half of derivative of e raised to the power of x, which is e raised to the power of x. Then we have e raised to the power of negative x, so its differentiation will be negative e raised to the power of negative x. Then this is the sine hyperbolic function. So here we have obtained that the derivative of the cosine hyperbolic function gives us the sine hyperbolic function, but there will be no negative sign in front. It will be simply a positive value. Let's try to find out the derivative of the tangent hyperbolic function or the hyperbolic tangent function. So we have derivative with respect to x of tangent hyperbolic x. So this is equals to, we have derivative with respect to x of the hyperbolic tangent function is given by e raised to the power of x minus e raised to the power of negative x divided by e raised to the power of x plus e raised to the power of negative x. Now all we have to do is find the derivative of this particular expression, and for that, what do we need to use here in order to find the derivative? So since this is in the quotient form, we have to use the quotient rule. So we will begin by taking the square of the denominator. So we have e raised to the power of x plus e raised to the power of negative x squared. And in the numerator, again we'll start with the denominator, e raised to the power of x plus e raised to the power of negative x multiplied to derivative with respect to x of the numerator, which is e raised to the power of x minus e raised to the power of negative x minus, you can start with the numerator, e raised to the power of x minus e raised to the power of negative x, and this will be multiplied to derivative with respect to x of the denominator, which is e raised to the power of x plus e raised to the power of negative x. So this will be e raised to the power of x plus e raised to the power of negative x times derivative of the exponential function e raised to the power of x is simply e raised to the power of x, and this will become positive. So here we have used the chain rule, minus e raised to the power of x minus e raised to the power of negative x multiplied to e raised to the power of x, which is the derivative of this exponential function, and derivative of e raised to the power of negative x will be minus e raised to the power of negative x whole divided by e raised to the power of x plus e raised to the power of negative x whole squared. Now let's simplify the numerator. So we have e raised to the power of x multiplied to e raised to the power of x, so that will be e raised to the power of 2x. Then e raised to the power of x multiplied to e raised to the power of negative x. So the multiplication, this is equals to e raised to the power of x minus x, which is e raised to the power of 0, and this gives us the value 1. So we have positive 1. Similarly, e raised to the power of negative x times e raised to the power of x, so that will be 1 plus e raised to the power of negative x multiplied to e raised to the power of negative x will give us e raised to the power of negative 2x minus, in other way we can also say that e raised to the power of x minus e raised to the power of negative x, so it's the same term getting multiplied to itself. So we are squaring this, we can apply the identity a minus b whole squared, so this will give us e raised to the power of 2x minus 2 plus e raised to the power of negative 2x whole divided by e raised to the power of x plus e raised to the power of negative x whole squared. Now when we solve the numerator, see all the e raised to the power of 2x terms and all the e raised to the power of negative 2x terms will get cancelled, leaving us with only 4 in the numerator. So we have 4 divided by e raised to the power of x plus e raised to the power of negative x whole squared. Furthermore, we can rewrite this expression as 2 divided by e raised to the power of x plus e raised to the power of negative x whole squared, means the same thing. And recall that this is simply the secant hyperbolic x squared, or we can say this is secant hyperbolic squared x. So this is the derivative of our tangent hyperbolic function. So we got quite similar to what we obtained for a trigonometric function. Recall the derivative of the tangent function. So that's equals to secant squared x. Quite similar. So it'll be easier to remember this. Now, what about derivative of the cot hyperbolic x function? What will be this particular value? Recall, if we consider simply the cotangent function, so that gives us negative cosec squared x. It should have something like cosec hyperbolic squared x. But what about the sign here? Will it be negative or will it be positive? So we need to check that out as well. So let's perform the derivative. So we have derivative with respect to x of cot hyperbolic x, which is equals to derivative with respect to x of what is cot hyperbolic x. So we have e raised to the power of x plus e raised to the power of negative x divided by e raised to the power of x minus e raised to the power of negative x. This is the cot hyperbolic function. So that means we need to find out the derivative using the quotient rule. So let's try it out. So we see that the derivative of the hyperbolic cotangent function, that is equals to negative cosecant hyperbolic squared x. So that means there will be indeed a negative sign. Next, we are left with now derivative of cosecant hyperbolic x. We need to determine the value of this particular derivative. So let's begin. So we take the derivative with respect to x of cosecant hyperbolic x, which is 2 divided by e raised to the power of x minus e raised to the power of negative x. While you can use the quotient rule, but for this particular example, I'm going to use the product rule on how to do that. So we know that 2 is a constant, so that can be pulled out of the derivative. So we have 2 times derivative with respect to x. So we have 1 divided by e raised to the power of x minus e raised to the power of negative x, which can be rewritten as e raised to the power of x minus e raised to the power of negative x whole raised to the power of negative 1. So we have taken the denominator to the numerator. This is done so that we can use the power rule. So this is actually, we have to use the chain rule. So if we assume that e raised to the power of x minus e raised to the power of negative x is equivalent to x, then we have something of the form x raised to the power of negative 1. So let's try to use the power rule. We have negative 1 multiplied to e raised to the power of x minus e raised to the power of negative x whole raised to the power of negative 1 minus 1 times chain rule, derivative with respect to x of our assumption, which is e raised to the power of x minus e raised to the power of negative x. So this is negative 2 times e raised to the power of x minus e raised to the power of negative x raised to the power of negative 2 times your derivative of this particular function will be e raised to the power of x plus e raised to the power of negative x. So positive is coming because we have e raised to the power of negative x. So there will be a minus 1 coming out as a result of the chain rule, which gets multiplied to this negative to become positive. So let's rearrange everything. So this will be negative 2 times. So we have 1 divided by e raised to the power of x minus e raised to the power of negative x whole squared multiplied to e raised to the power of x plus e raised to the power of negative x. So this can be now rewritten as negative times So let's say 2 divided by e raised to the power of x minus e raised to the power of negative x. So this will be one term multiplied to e raised to the power of x plus e raised to the power of negative x divided by e raised to the power of x minus e raised to the power of negative x, which will be equals to negative times. So this ratio 2 over e raised to the power of x minus e raised to the power of negative x. So that is the cosecant hyperbolic function times, and this is the hyperbolic cotangent function. So this is the derivative of our cosecant hyperbolic cosecant function. And if we want to remember this formula, the easy way would be to remember the derivative of the cosecant function, which is negative cosecant x times cotangent of x. It has the very similar form, so quite easier to remember, and we also have the negative sign as well. And next we want to perform the derivative of the hyperbolic secant function. Recall that if we take the derivative with respect to x of the secant function, that gives us secant of x times tangent of x. So that means this is also going to have something of the form secant hyperbolic x times tangent hyperbolic x. But the question is, what about the sign? Is it going to be positive or is it going to be negative? So this we need to confirm. So let's begin by taking the derivative of the hyperbolic secant function. So the hyperbolic secant function, which is the reciprocal of the hyperbolic cosine function, this is 2 divided by, we have e raised to the power of x plus e raised to the power of negative x. Similar to the previous problem, we can also rewrite it as derivative with respect to x of e raised to the power of x plus e raised to the power of negative x raised to the power of negative 1. So let's use the chain rule and the power rule in conjunction to find out the value of this particular derivative. So that means there will be a negative sign here. So this is something worth remembering. So we have only two cases where we need to be very careful. One case is when we take the derivative with respect to x of the cosine hyperbolic of x. This is going to be positive sine hyperbolic x. Because if we take derivative with respect to x of cosine function, so that gives us negative sine function. So this is where we need to be careful that this is not negative, but instead it is positive. And this is another case where the derivative of the hyperbolic secant function has the very familiar form with the derivative of the secant function, except for there will be a negative sign. Right. So now that we have covered the derivative of all the 6 hyperbolic trigonometric functions, now next we need to talk about the inverse hyperbolic trigonometric functions. Now before doing that, we need to cover one more thing. So we have the hyperbolic sine function, so that is given by e raised to the power of x minus e raised to the power of negative x divided by 2. So let's square both sides. So we have sine hyperbolic squared x, so this will be e raised to the power of x minus e raised to the power of negative x whole squared divided by 4, which will give us e raised to the power of 2x minus 2 plus e raised to the power of negative 2x whole divided by 4. And our cosine hyperbolic function, so that's equals to e raised to the power of x plus e raised to the power of negative x whole divided by 2. Again, squaring both sides, we have hyperbolic cosine squared x equals to e raised to the power of 2x plus 2 minus e raised to the power of negative 2x over 2. So now what we will do here is we take the cosine hyperbolic square x function minus sine hyperbolic squared x. So let's do that. So we have for the cosine function, we have cosine hyperbolic function e raised to the power of 2x plus 2 minus, oh, this is positive, plus e raised to the power of negative 2x divided by 4 minus the square of the hyperbolic sine function, which is e raised to the power of 2x, negative 2 plus e raised to the power of negative 2x divided by 4. So let's combine them. We have e raised to the power of 2x plus 2 plus e raised to the power of negative 2x minus e raised to the power of 2x plus 2 minus e raised to the power of negative 2x. So the few of the terms will get cancelled out, and this leaves us with 2 plus 2, which is 4 over 4, and this is simply equals to 1. So this is an extremely important identity where the difference in square of the hyperbolic cosine and the sine function gives us the value 1. So we will be using it. This will be used when we find out the differentiation or the derivative of the inverse hyperbolic trig functions. Let's start with that. So let's begin with the derivative of the inverse hyperbolic sine function. So for this, we have to perform an implicit differentiation here. So we begin by considering let y equals to the inverse hyperbolic sine function. Then taking the hyperbolic sine function on both sides, so we have sine hyperbolic of y will be equals to x. Next, we differentiate both sides with respect to x. The derivative with respect to x of hyperbolic sine function equals to derivative with respect to x of our function x, that's equals to 1. Now, we have derivative with respect to x of our hyperbolic sine function, so that's equals to cosine hyperbolic x. So since this is y here and we're differentiating with respect to x, so we will have cosine hyperbolic y instead of x, but we need to use the chain rule and multiply it to the derivative of y with respect to x. Dy over dx, or derivative of y with respect to x, will be equals to 1 over hyperbolic cosine function. Now we can use the identity. We have hyperbolic cosine squared function minus hyperbolic sine squared x y is equals to 1. So from here we can find out cosine hyperbolic squared y, which will be 1 plus sine hyperbolic squared y, or simply the positive square root of sine hyperbolic squared y plus 1. Replacing this value, we have square root of sine hyperbolic squared y plus 1, but we already considered sine hyperbolic y is equals to x. So this will give us x squared plus 1. So that means the derivative of the inverse hyperbolic sine function, so that's 1 over square root of x squared plus 1. So this is the first one. Let's now talk about the derivative of the inverse hyperbolic cosine function. Same procedure, we need to consider that y is equals to cosine hyperbolic inverse of x. We'll take the hyperbolic cosine function on both sides, which will give us cosine hyperbolic y is equals to x, taking the derivative with respect to x. Cosine hyperbolic y is equals to derivative of x with respect to x. So derivative of the hyperbolic cosine function, that is simply positive sine hyperbolic y times dy over dx, which is equals to 1. And this gives us derivative of y with respect to x is equals to 1 divided by sine hyperbolic y. So we have cosine hyperbolic squared y minus sine hyperbolic squared y equals to 1. So sine hyperbolic y will be equals to cosine hyperbolic squared y minus 1, and we have to take the positive square root, and this will be equals to square root of, so in place of cosine hyperbolic y we'll take x, so this will be x squared minus 1. So this is the derivative of our hyperbolic cosine function. Next, we talk about the derivative of the inverse hyperbolic tangent function. So let inverse hyperbolic tangent function be equals to y, or simply x is equals to the hyperbolic tangent function of y. Taking the derivative on both sides with respect to x gives us 1 equals to, so what is the derivative of the hyperbolic tangent function? So that is secant hyperbolic squared y times dy over dx, and dy over dx, that will be equals to 1 over secant squared y. Now we need to use an identity. We know that hyperbolic cosine squared y minus hyperbolic sine squared y is equals to 1. We'll divide both sides with hyperbolic cosine squared y. So this will be 1 minus, now we have a ratio of sine over sine hyperbolic over cosine hyperbolic, so that will be tangent hyperbolic squared y, and 1 divided by cosine hyperbolic squared y, which is the secant hyperbolic squared y. And we assume that tangent hyperbolic y is equals to x, so this will be 1 minus x squared. So this is the value of secant hyperbolic squared y. So our derivative of the hyperbolic tangent function, that will be equals to 1 divided by, we have secant hyperbolic squared y, and this is simply 1 minus x squared. Next, let's try to find out the derivative of our hyperbolic cotangent inverse function. So we'll begin by supposing y is equals to cot hyperbolic inverse of x, or simply cot hyperbolic y is equals to x. Taking the derivative on both sides with respect to x, so we have derivative with respect to x of hyperbolic cot function, which is equals to derivative of x with respect to x. So derivative of the cot hyperbolic function will be negative cosec hyperbolic squared y times dy over dx, which is equals to 1. So that means dy over dx will be equals to negative 1 over cosec hyperbolic squared 1. So we'll use the identity cos hyperbolic squared y minus sine hyperbolic squared y is equals to 1. Now we'll divide both sides with sine hyperbolic squared y, so this will become, so cos over sine, that ratio is cotangent hyperbolic squared y minus 1 is equals to cosec hyperbolic squared y. So cot hyperbolic, so we y, that's x, so this will become x squared minus 1, which is the value of cosec hyperbolic squared y. Now let's replace this value here. So that means the derivative of cot hyperbolic inverse function, that will be equals to negative 1 divided by x squared minus 1. Now let's determine the remaining two inverse trig functions. So we have derivative with respect to x of secant hyperbolic inverse of x. Same, we'll perform the implicit differentiation. So let y be equals to secant hyperbolic inverse of x. Taking the secant hyperbolic function of both sides gives us secant hyperbolic of y is equals to x, taking the derivative with respect to x. So we have secant hyperbolic of y is equals to 1. So what is the derivative of the secant hyperbolic function? So this is negative secant hyperbolic y times tangent hyperbolic of y times derivative of y with respect to x, which is equals to negative 1. Or we get derivative of y with respect to x, that will be equals to -1 divided by secant hyperbolic y times tangent hyperbolic of y. So we can use the identity that 1 minus tangent hyperbolic squared y is equals to secant hyperbolic squared y. So here, solving for tangent hyperbolic squared y, we have 1 minus secant hyperbolic squared y, and tangent hyperbolic of y will be, we'll take the positive square root, 1 minus secant hyperbolic squared y. And we have taken the secant hyperbolic function as x, so the tangent hyperbolic function of y is simply given by square root of 1 minus x squared. So let's use this value, and this will give us the derivative of secant hyperbolic inverse x, which will be equals to -1 divided by, we have secant hyperbolic of y, so this will be x. We'll take the absolute value multiplied to square root of 1 minus x squared. So this is the derivative of the inverse secant hyperbolic function. Let's go to the final one. Derivative with respect to x of cosec hyperbolic inverse x. So let y be equals to cosec hyperbolic inverse x. So cosec hyperbolic of y will be equals to x. Taking a derivative will give us negative cosec hyperbolic y times cot hyperbolic y times derivative of y with respect to x is equals to 1. Solving for dy over dx, that will be equals to -1 divided by cosec hyperbolic y times cot hyperbolic y. So we have a value for cosec hyperbolic y, so this will get replaced with x. Now we'll need to find out cot hyperbolic y. So that means derivative of the hyperbolic cosec squared function, so this will be equals to -1 divided by absolute value of x multiplied to x squared plus 1. So we will use our knowledge on the derivatives of the hyperbolic functions and its inverse to solve few problems. So this is the first problem. We need to find the derivative of hyperbolic cosine of x raised to the power of x. So recall that derivative of the hyperbolic cosine function, so that is equals to sine hyperbolic of x. So here we do not have an x here, we have x raised to the power of 8. So we'll need to use the chain rule. For that we will assume that x raised to the power of 8, if it were x, then this will give us sine hyperbolic x. But since this is not, we need to multiply it to the derivative of x raised to the power of 8. So this is fairly simple. We can use the power rule. This will give us 8 times x raised to the power of 7 multiplied to hyperbolic sine of x raised to the power of 8. So this is the derivative of a given hyperbolic cosine function. Let's do another problem. Well, we need to find out the derivative of x squared with hyperbolic secant of 2x. So that means we begin by first performing the product rule. So we'll take x squared as the first function. So this will multiply to the derivative of our second function, which is hyperbolic secant 2x. Plus, we take the second function's hyperbolic secant 2x and multiply it to the derivative of our first function, which is x squared, which will be equals to x squared times. So we have derivative of the hyperbolic secant function, assuming this is equivalent to x, and this will be negative secant hyperbolic of 2x times tangent hyperbolic of 2x. And this is multiplied to derivative of 2x. What we've done is applied the chain rule here. Plus secant hyperbolic of 2x times derivative of x squared is simply 2x. So this gives us negative. So from derivative of 2x we have 2, because derivative of x with respect to x will be 1. And we have an x squared here, so negative 2x squared times secant hyperbolic of 2x times hyperbolic tangent of 2x plus 2x times secant hyperbolic of 2x. So this is the required derivative. Let's move on to the next problem. So let's find out the derivative of the natural log of sine hyperbolic of 6x. So we remember derivative of the logarithmic function, so that's the outermost function. We have to use the chain rule here. We'll assume sine h, the hyperbolic sine of 6x as x. So that should give us 1 over x. So x here is hyperbolic sine of 6x. Then we need to multiply it to the derivative of our assumption, which is sine hyperbolic of 6x. This will be equals to, we have sine hyperbolic 6x times derivative of the hyperbolic sine function gives us the hyperbolic cosine function, and then again this will be multiplied to derivative of 6x, which will give us simply 6. So the final answer will be 6 times. So we have a ratio cosine over sine, which is the hyperbolic cot function or the cotangent function. So we have 6 times hyperbolic cotangent of 6x. So this is the required derivative. Let's move on to the next problem. So we have a function p of x given by the inverse hyperbolic cotangent function of 3x minus 2. We need to find its derivative with respect to x. So first let's note down the derivative of our hyperbolic cot function. So this is given by negative 1 over x squared minus 1. So we have p of x given by the hyperbolic cot of 3x minus 2. So its derivative with respect to x will be equals to negative 1 divided by, so this will be treated as x. So we have 3x minus 2 whole squared minus 1. But since this is not x, so we'll multiply it to the derivative of 3x minus 2. So derivative of 3x minus 2, so that will be negative 3 divided by 3x minus 2 whole squared minus 1, which is the required derivative. Let's move on to the next and the final problem. So we need to evaluate the derivative of hyperbolic tangent function of x cubed whole squared with respect to x. The first, here we have to be a little bit careful here. We have some function raised to the power of 2. That means we need to apply the power rule first. So that will be simply 2 times the function, the inverse hyperbolic tangent of x cubed whole raised to the power of 2 minus 1 multiplied to derivative with respect to x of the function inverse tangent hyperbolic of x cubed. So this will be now 2 times the inverse hyperbolic tangent of x cubed times, so what is the derivative of the inverse hyperbolic tangent function? So let's make a note of that. So derivative of our inverse hyperbolic tangent function, so that's given by 1 over 1 minus x squared. So we'll use this particular fact. So this will give us 1 over 1 minus x cube squared. Here we are treating x cubed to be equivalent to x, but since this is not, we need to multiply it to the derivative of x cubed. So everything is done. So our final answer will be, so derivative of x cubed will be 3, this will be 3x squared. So this 3x squared multiplies to 2 to give us 6x squared times the inverse tangent of x cubed whole divided by 1 minus x raised to the power of 3 times 2 will be 6. So this is how we can obtain the derivative of hyperbolic functions as well as hyperbolic inverse trig functions. Thank you.